Hello everyone, welcome to the first lecture of module 4, which is on transmission line parameter evaluation, in which we will start with a basic understanding of what the transmission line parameters are and what is line resistance to be specific, how it is evaluated in this NPTEL course on power network analysis. Till the last lecture, we had covered with our first 3 primary modules, and we finished up with synchronous generators, where the last part discussion was on economics involved behind scheduling 3-phase synchronous generators and how to ensure parallel operation of these generators when they are connected to a power network serving distinct loads present at different points in the network. So, this being the first discussion for the module transmission line parameters. So, we will take up our discussion on line resistance by understanding few basic preliminaries of the requirements of transmission lines and why they are needed. So, it is pretty well understood by now that our generators, which are placed far off in terms of geographical location, placed far off to the load locations, it is impossible or not an easy task to say to have generators directly feeding in the consumers or the loads. The loads again could be of residential type, industrial type, etc. So, that is where we would need a corridor, and that corridor happens to be these transmission lines or distribution line for that matter, which often we see them as overhead lines if we traverse or travel by road, and we also happen to see certain cables laying near our residential community. Now, transmission line is the line where often you would see the overhead line arrangement, because transmission lines or network operate at high voltages, and the reason for scaling up or amplifying up the generation power to high voltages is to minimize the I square R loss or the copper loss which is going to happen in the conductor. So, by amplifying the voltage level at the same power requirement, less current needs to flow in the conductor, which in a way minimizes the I square R component. Whereas, for distribution lines or for distribution networks, the voltage level is low, or the voltage level is again scaled down by step down transformers which get their power from the transmission network, because our loads, not all of our loads can consume power at high voltages. So, we need those distribution networks, and mostly from the perspective of aesthetics, we often see the cables being placed instead of overhead distribution lines, although certain societies, cities, they still have this overhead distribution network perspective, but from the aesthetics perspective, cables are replacing these overhead distribution lines day by day, because the voltage requirement is low and hence the insulation requirement is low, the safety concern is relatively low, although there are issues with cables compared to overhead lines in terms of filtering out or monitoring out any disturbance or fault in the cable perspective. But given that apart, we will for our discussion mostly focus on the transmission lines, which are usually overhead in nature, and irrespective of whether these are overhead lines or cables, almost all these cables or lines, they have 4 common attributes or parameters from the electrical engineering perspective. The first 3 are shown here, the first 2 being the series elements, which are resistance and inductance. The third one, which is in yellow, is the shunt element, the capacitance. And additionally, we also have a 4th element, which we call as conductance, which is basically inverse of the resistance, and also it happens to be a shunt element. In this module or in this transmission line parameter evaluation, we will keep our focus on the first 3. The reason why the last one we would not consider is because of the fact that its evaluation is first of all difficult, its modeling is difficult, and even if it were to be modeled or evaluated, its quantum or effect is negligible or marginal on high voltage transmission network. Now, before we proceed further, on discussing what is line resistance, and then followed by the upcoming lectures on line inductance and capacitance. One thing we should note or make a point of it is why the resistance and inductance happen to be series elements and why capacitance happens to be a shunt element. For the time being, what I can only explain briefly or state briefly is that resistance and inductance, they are inherently there because of the line conductor or the attribute of the conductor itself. So basically, the property is exhibited by a line which is conducting power or transmitting current at high voltage or low voltage. Certain phenomena happen because of which the line tends to exhibit the resistance property and inductance property, and it is mostly related only to the inductors or inductors nearby that actual inductor. In case of capacitance, things become little different in the sense capacitance is also a property of the line which is conducting current or transmitting power, but it also gets influenced by nearby charged or conducting bodies. These conducting bodies need not be parallel line conductors. For example, the presence of earth or nearby insulating material or nearby charged body like a tree or a tower or a house or a wall or a humid moist surface near the line conductor, that can also influence the line capacitance. In addition to its own property, capacitance also gets influenced by nearby charged bodies which need not be conductors in themselves. That's the reason why capacitance is often related as a shunt material, something which is protruding out of the conductor and then is getting placed in parallel to the earth or in conjunction to the earth. And that's the reason why we consider capacitance to be a shunt element, while resistance and inductance, they mostly being the attributes limited to the conductors themselves, these often appear to be as series and series elements. Similar logic, what we discussed for capacitance is also applicable for conductance, but since we won't be focusing much on conductance, so whether it is shunt or series is not a point of concern in this particular module. So conventionally, when the power network evolved in 1800, 1900 era, the initial transmission line conductors, they used to be made of copper because that was one of the most well-known conductor or material which has good electrical property. But the issue with copper wires or conductors was copper is heavier in weight and hence the line span could not be large, and that's the reason why over the period of time aluminium has entirely replaced copper conductors, because for the same current carrying capacity or for the same voltage gradient capacity, aluminium tends to have low cost and low weight, which in a way makes life easier for transmission network owners and operators to erect transmission towers and corresponding lines. And that's the reason why aluminium has completely replaced copper conductors. But aluminium also has its own pitfall, in the sense aluminium does not tend to have the same mechanical strength which a copper conductor could have for the same resistance, same conductivity, same current. And another reason why aluminium has replaced copper conductors entirely is for the same current carrying capacity, aluminium could have a larger diameter. For the same resistance, aluminium could have a larger diameter, which in a way tends to reduce the voltage gradient on the surface of the conductor, and that helps in reduction of corona loss. Please have patience. We will discuss corona loss in detail in the next few slides to come. Now, I mentioned one thing, that because of larger diameter, the voltage gradient on the surface of conductor tends to be lower. Now, what is voltage gradient? So, let's briefly talk about voltage gradient for time being. So, voltage gradient in a very nutshell is nothing but the rated voltage at which the line is supposed to carry the power or the current divided by the surface area of the conductor. If there is a conductor of common resistance with larger surface area, it would inherently mean that the voltage gradient on surface of conductor would be smaller, meaning the potential difference which nearby placed bodies would see per area surface of the conductor would be lower, and hence the possibility of additional discharges happening a nearby medium, specifically air ionizing itself, would be lower. That's the reason why aluminum conductors are replacing or have replaced copper conductors entirely. There are different types of alloys which are being used along with aluminum conductors to enhance the mechanical strength as well as improve the electrical property. One such common conductor which is common in power network domain is in short known as ACSR conductor, which is nothing but aluminum conductor with steel reinforced or aluminum conductor steel reinforced ACSR. What does ACSR mean? The cross-sectional view of a typical ACSR conductor is shown over here, where the black strands or conductors, these are made up of steel, and the near or periphery conductors which are wound along the steel conductor are made up of aluminum or corresponding alloy. Now, with this sort of a stranding, ensuring that the current carrying capacity of the conductor doesn't change, with this sort of a stranding, since steel has higher mechanical strength compared to aluminum, and if I have a conductor and I wound another small wire or thin wire around that stronger conductor, the thinner wire mechanical strength also increases, in the sense if I have to break the wire apart, I will have to pull it harder compared to just a case where if I take a small copper thin wire and I pull it apart, probably it can break. But if I wound around that small thin copper or aluminum wire around the iron core and now I try to pull it up, the wounding of the core or the conductor increases its mechanical strength. So that's the reason why ACSR conductors are pretty common. And we also have additional arrangements specifically for operating voltages beyond 230 kV line to line. It is preferred to have more than one conductor per phase. At the outset, it would appear that, oh, if this is one such ACSR conductor, for three-phase system, there could be three such conductors in different arrangements for phase A, phase B, or phase C, or if you call phase Y, phase R, phase Y, phase B, then you would have three such conductors for individual one such phase. For higher operating voltages, instead of having one such conductor for every such phase, there are more than one conductors placed in some arrangement which pertain to one single phase. So let's say if I have to draw a 4 bundled conductor for each bundle representing one phase, then this is one such bundle, and often you would see such an arrangement in overhead transmission towers operating beyond 220 kV, 400 kV, where there are 12, 13, usually there are multiple of threes, 12, 15, 18, 21 conductors running in parallel. And if we were to assume that 21 conductors pertain to one phase, no. There are bundles which pertain to one such phase. And the reason for bundling is that the overall line reactance, which I would say line inductance as well as capacitance, that tends to go down. The overall voltage gradient tends to go down, which reduces the effect of corona loss and so on. So bundling, it has its own issues, but then also provides additional advantages in terms of reduction of corona loss and reduction in effective line reactance. So having talked about corona loss, what actually is corona loss? It's not the novel 2019 COVID virus which refers to corona. This electrical corona has been there for centuries now, and it particularly refers to the fact or the event when around a conductor which is having higher voltage gradient, or the potential difference, or the potential is very high on the conductor, the nearby air tends to get ionized under certain conditions. And this ionization of air is because of high voltage gradient, which in a way leads to electrical breakdown of air. Air is a bad conductor of electricity. It's actually a very good insulator. But beyond a particular voltage gradient or a particular voltage, air also loses its insulation property and tends to behave as a conductor. And this conduction property of air leads to leakage current. This leakage current originates from the conductor which is having high voltage gradient, and since the air is now ionized, the current which is originating from the conductor gets leaked out to nearby passages or nearby electrical bodies. So for example, if there is a long tree with large branches hanging around or there are transmission lines hanging around a large tree with large branches, then because of weather or bad weather or air, the branches may touch these transmission lines and that may act as good connecting bodies. So eventually that's the reason why for transmission line erection, right of way is needed, and longer trees or higher trees are pruned down to avoid such disasters. That the tree itself might get burned because of coronal loss event, and it happens often if planning is not proper. So this current is getting leaked out through air to nearby medium, and on a extremely hot and dry weather, or during dampy conditions, during there is high fog or there is lot of rain or lot of humidity in the air, for conductors operating at higher voltages, one might often hear a hissing sound or a visible spark glowing around the conductor, which essentially indicates that the air is getting ionized. It's actually a miniature arcing event which is happening. The air is getting ionized, and through this arcing or sparking, the leakage current is getting passed on to nearby insulator or flashover, and etc. etc. So, in order to reduce this corona event, the voltage gradient should be minimized. Again, there is a compromise that why should we then operate at higher voltages? Higher voltages are needed to minimize copper loss, but then higher voltage gradient should not be so high that corona loss events become higher. So, to have a trade-off, we expect as electrical engineers that the conductor should have smaller diameter, but then smaller diameter would increase the surface area, so diameter should be as large as possible, so the area, surface area goes up, but then that would increase the cost of conductor, make the mechanical strength a concern. So to have a reduced corona loss, bundling is one such measure, and that's the reason why two or more than two conductors are assigned for a particular phase conduction. And this corona loss, since it is a leakage current which is passing on to nearby a medium, it's very similar to I square R loss, which is called as a real power loss. Compared to copper loss, the corona loss is very small, and in transmission line conductors, by proper design, by proper operation, by proper right of way, this can be minimized. Line conductance parameter accounts mostly for this corona loss and any other leakage current that happens due to corona. The modeling of corona loss itself is difficult. Even if it is not to be difficult, it's very small, and that is the reason why line conductance modeling is often ignored in transmission line parameter evaluation. Even if it were to be modeled, its modeling would be very rigorous, because corona is not a continuous event which is happening. It's happening, or its event occurrence itself is an uncertain event, because it depends on weather conditions, nearby conductors charging, discharging, power flow happening, line switching on and off. So several such uncertain factors influence the occurrence of corona. So for modeling it, one has to understand how it actually happens, when it is going to happen. So that itself is difficult to account for. And that's the reason why we would not consider line conductance evaluation as part of our discussion. We would also discuss or look at certain properties of high voltage lines in terms of their electrical field and magnetic flux lines, which help in quick understanding of where does this line inductance or line capacitance property come from. So let's look at that. So certain properties of transmission lines, they can be very well explained by associated electric and magnetic fields. What I have here is a single phase 2 circuit line, in which by single phase 2 circuit line I mean one conductor is the live conductor at a given point of time, whereas the other conductor is the return path for the live conductor. And since we are talking about a transmission line which is operating at a AC voltage, so it might happen the role of live and return wire, they may change in a typical cycle of AC conduction. So for this current carrying circuit, which is single phase 2 wire circuit, there are certain lines which have been shown. These are called as magnetic flux lines and electric flux lines. Magnetic flux lines, they happen to be concentric flux lines around the current carrying conductor, whereas electric field lines or flux lines, they always originate from a charged body or a conductor, and they terminate at another charged body or a conductor. So that's the reason why you would see the first 4 lines here. They are originating from one conductor and terminating in another conductor. The arrows are not shown. I will explain that in a moment. There are other electric field lines which are originating from the conductor. Let's say the conductor over here, the line over here, but they are spreading far off, and they may reach or may not reach the same line which is shown over here in the return path. These lines may also be protruding into the earth, the surface. The earth's surface is also a neutral or electrically charged neutral body. So how come these field lines or flux lines come from? So let's look at that briefly for a moment. If we recollect our synchronous generator discussion, we have talked about magnetic field lines or flux lines at length, wherein we understood that magnetic field lines, they are always closed loop lines, they are always closed loop flux lines, and they are always concentric around the current carrying conductor. So let me explain how this is happening. So let's say at a given instant of time, this conductor is carrying current out of the plane of the surface, and the other return conductor is carrying same quantum or magnitude of current, but the direction is reversed. So the current is into the plane of the slide or the board. Now, if I remember, or if you recollect the right hand rule, for conductor which is carrying current out of the plane of the slide, if the thumb points to the direction of current, the fingers would curl in a counterclockwise direction for this current carrying conductor. So essentially at this instant, the magnetic flux lines are in a counterclockwise direction as shown over here. The same logic if we apply to conductor which is carrying current into the plane of the slide with thumb pointing inside the slide, the fingers curl in clockwise direction. So magnetic flux lines, they are actually in this particular orientation. So if I superimpose or combine the magnetic flux lines because of these two current carrying conductors, essentially it appears that there exists a fictitious magnet whose analogous north pole is on the top, analogous south pole is on the top, and the flux lines, they originate from the north pole outside a magnet and they terminate at the south pole outside a magnet. So this two conductor arrangement, it may appear to be resembling a corresponding analogous magnetic electromagnet. So that's the reason how magnetic flux lines exist. Electric field lines, as I said, they always originate from one conductor and terminate at the other conductor. And by conductor, I mean if they are carrying current, current carrying is nothing but rate of change of conducting charges. I would not say these are negative charges or positive charges, but conventionally speaking, if current is flowing in the conductor, current is nothing but dq by dt, where q is the charge, positive charge present in the conductor. If I associate current in this conductor which is carrying current out of the slide to be equal to analogous positive charge at a given instant of time, then for the another conductor which is carrying current into the slide, I can associate this current to be carrying or to be present because of a negative charge, because the current directions are reversed. Now, if I have this analogy in place, then electric field lines, they would originate from positive charge, terminate on negative charge. So it's pretty clear that in this particular figure, the electric field lines at this instant of time are as per these arrows. In the second half cycle of the AC generation or AC wave, the moment these currents reverse their positions, this current becomes dot and this becomes a cross. Though the charges become negative and positive, the electric field lines, instead of being from right to left, they would change their orientation from left to right. So in an AC circuit, the magnetic field lines, electric field lines, they can exist, they do exist, and you'd be surprised to know, not surprised, there's a very well-defined logic for that, which we will discuss at length in transmission line performance evaluation, which is going to be the next module, that majority of quantum of power which is transmitted through these transmission lines is because of these magnetic field lines, electric field lines. If they would not have existed, our conductors would not have been possible to transmit higher quantum of power from so large distances. So with this, let's now understand how do these flux lines result in inductance and capacitance. So current carrying conductor which is varying because it is a AC current, is varying in time, causes a change in number of linkages of magnetic and electric field lines or flux lines. And by Faraday's law and Lenz's law, we understand or know, thanks to transformer discussion, synchronous generator discussion, that a change in magnetic flux linkage in a circuit, it tends to induce a voltage in the circuit which is proportional to the rate of change of flux. Essentially, the induced EMF or V, E or V, whatever you represent, is proportional to N d phi by dt. The Lenz's law associates a negative sign here. So if flux linkage, magnetic flux linkage is varying in time, the corresponding voltage or circuit would also have an induced EMF or a voltage. So that is attributed by the property of inductance. And capacitance, on the other hand, is counter product or I would say a complementary feature to inductance. If inductance is because of change in magnetic flux lines or field lines, capacitance is because of charge developed due to time varying electric field lines or flux lines per unit potential difference. So that's the reason why L is associated mostly with the magnetic property or magnetic behavior of current carrying conductor, whereas capacitance, which is usually denoted by C, is because of the electric field lines or flux lines represented by these current carrying conductors. So we'll discuss these phenomena, behaviors at length in the upcoming lectures. For timing, we'll focus on resistance. Resistance, unlike inductance and capacitance, is very simple to understand because it is property of the conductor itself. And superconductors, for information, tend to be conductors whose resistance is very low, or researchers are trying to have or create conductors whose resistance is perfectly zero. So lossless conductors, which might come up because thanks to those researches. But typical conductors, practical conductors, they tend to have resistance. And what is resistance? Is essentially obstruction to the flow of current in a conductor. So the resistance that we often see or discuss is often called as the DC resistance of a conductor, which is true or applicable or provided by the manufacturer only when the current distribution of the conductor is uniform. And this resistance tends to be dependent on certain properties. It depends on the line length of the conductor. It also depends on the cross-sectional area of the conductor, and it also depends on the resistivity of the conductor at a given temperature. Different materials, copper, aluminum, steel, they have different resistivities, and hence for the same cross-sectional area, for the same length, different materials tend to have different resistance values. One big thing we can also observe here, that if the area tends to increase, which is resulting in increase in the denominator of this number, the corresponding resistance would decrease. So basically resistance is inversely proportional to area, and as the line length increases, the resistance tends to increase. So with this aspect in mind, the length and the cross-sectional area, which would become obvious in the next slide, the value of R, it is actually affected by the nature of current flowing in the conductor, whether it is a AC current or a DC current. If the DC current is flowing in a conductor, then the value which is specified by the manufacturers, the one that we calculate for given area cross-section L and resistivity, we often would always evaluate the DC resistance. The flow of AC current, it changes the resistance value by a bit. The conductor spiraling, as I mentioned, increases the mechanical strength. So spiraling tends to increase the effective length of resistance. So overall length may be lesser than the actual length which has been spiraled. So effective resistance tends to go up there. Operating condition of weather also increases the value or decreases the value of resistance. Like in a hot, dry weather, the resistance value could be higher, whereas in a cold, dense weather, the corresponding resistance could be lower. So spiraling, as I mentioned, it tends to increase the overall resistance of the conductor because spiraling increases the conductor length. So DC resistance, which is given by the manufacturer or evaluated by formula, may not be same as the actual resistance attributed by the corresponding resistance. With increase in temperature, resistivity tends to increase or decrease, which is usually proportional for practical cases. So if the temperature is increasing, the corresponding resistance would also increase accordingly. Tc is the temperature constant for a given conductor of a typical material. For AC current flow, there is something which is known as skin effect. For compared to same quantum of AC current and same quantum of DC current, if the same conductor carries AC current and DC current, the AC current flow would increase the resistance value, and it happens because of skin effect. What is the issue, or what is the nature of skin effect? As the term skin effect says, the current, instead of being uniform, which is a necessity while definition of DC resistance, current distribution, instead of being uniform in the cross-section of the conductor, the skin effect results in more current flowing at the periphery of the conductor, lesser current at the center. So in a result, the current density at center is lower, the current density at the periphery is larger, and that happens when AC current flows. Reason: the overall inductance is more at the center, which in a way also is analogous to inhibiting the flow of current or inhibiting the rate of change of current. So inductance at the center tends to be more. So current, it has to flow through the conductor, so more of it gets distributed at the periphery or at the surface of the conductor, which in a way results in reduction of the overall cross-sectional area. So the denominator in rho L by A, R is equal to rho L by A, the overall A tends to go down, so overall resistance tends to go up. So AC resistance is always more than the DC resistance, and calculating overall actual AC resistance is not an easy job, because again, modeling or countering skin effect requires a lot of detailed analysis. That's all for today's lecture. We will take up the discussion on evaluation of inductance because of internal magnetic flux in the next lecture. What is internal magnetic flux, external magnetic flux? We'll discuss that when the appropriate time comes in. Thank you.